You just built a brilliant, custom-manufactured hardware prototype. It looks like a professional product, but here is the harsh reality of hardware engineering. A beautifully designed PCB is completely useless if your software gets stuck in an infinite loop, drains your batteries in 12 hours, and sends an autonomous AI agent into a death spiral that nearly blows your API budget. Welcome to part 2 of the TerraBlade Modular Soil Scout series. Today, we are transforming a messy single-file Arduino sketch into a bulletproof, fail-safe, object-oriented C++ codebase. And I tried to let an AI do all the work with mixed results. Let's dive in. But really quickly, guys, I want to ask a massive favor. If you get value out of this deep dive engineering series, please hit that like button and subscribe. Channels like this survive entirely on your support, and it seriously means the world to me. I personally read every single comment, and I promise you, I listen to your feedback and I build it directly into future projects. Okay, let's fix this software. Basic Arduino projects usually dump 500 lines of code into a single .ino file. That spaghetti code is a nightmare to maintain. To build a reliable product, we have to practice strict separation of concerns. Before I even brought AI into the mix, I manually scaffolded our Platform.io project into 5 isolated components. I actually abstracted this architecture from several of my previous proof of concept tutorials. If you want to see exactly how I built the initial logic, check the links in the description. Now, to make things interesting, I decided to use an AI coding agent to finish this project. I loaded up OpenCode, connected it to Hugging Face using the massive Qwen 3 480 billion parameter model, and gave it full terminal superpowers. But then, disaster struck. I walked away, and the AI fell into an agentic death spiral. Embedded C++ development relies heavily on specific hardware states. When the AI encountered a cryptic compiler error regarding hardware mocks, it panicked. It hallucinated fixes, deleted config files, and burned through hundreds of API calls trying to brute force a solution. Luckily, I had a hard $10 limit on my Hugging Face account. If I had an open-ended API key plugged in, I could have easily woken up to a $500 bill. Now, don't get me wrong here, I am not dismissing fully autonomous AI. If you are building a brand new greenfield project or a standard web app, agents are absolutely incredible. I actually built this complete React Minesweeper game using a local AI without writing a single line of manual code. I'll leave a link to that GitHub repo in the description. And setting this up for your own projects is super easy. You just generate an API token on Hugging Face, authenticate the OpenCode CLI in your terminal, and run the init command to generate your agent's system prompt. You can even tweak your JSON config to play a custom sound effect when the AI finishes a task. But here is the catch. Embedded C++ is a completely different beast. When you combine highly specific hardware states with an already half-built Platform.io project, a fully autonomous agent can lose its mind. So I pivoted. I completely stripped the AI of its terminal superpowers. Welcome to the Driver and Navigator AI coding workflow tutorial. The AI acts as the navigator, writing the complex C++ logic using Qwen 3.6 for C++ microcontroller programming. I act as the driver, manually compiling the code and running the tests. This completely mitigates the death spiral. But before we talk about compiling code, we need to talk about where this code lives. If you are pushing data to the cloud, your Wi-Fi signal has to punch through wet mud. A cheap breadboard simply cannot handle this. You need a professionally manufactured board with proper impedance matching for stable Wi-Fi transmission. And that is exactly why I use PCBWay, the sponsor of this video. PCBWay manufactured our brilliant 3-in-1 panelized TerraBlade motherboard. By using their panel by customer feature, we fit the radio, the power hat, and the sensor blade all onto a single 100 by 100 millimeter square, saving a ton of money on setup fees. They also provide precision stainless steel stencils, and their turnkey PCBA servers can even source your components and do the microscopic SMD soldering for you. For professional-grade IoT hardware, you absolutely need PCBWay. Check the link in the description to get your custom boards ordered today. Okay, back to the software. Flashing code to an ESP32 takes time and slowly degrades the flash memory. We are using test-driven development for embedded C++. We are going to test our hardware logic without actually using the hardware. I set up Platform I/O native unit testing with Arduino Fake. If you're wondering how to mock Arduino functions in Platform I/O, I created a universal helper file that tricks my desktop computer into thinking it has GPIO pins and an I2C bus. We can now run our ESP32 unit tests with the Unity test runner directly on a PC in milliseconds. Next, I had the AI code the sensor component. Our TerraBlade uses a TLC55 timer to convert soil moisture into a high-frequency 2.1 MHz signal. But we need to maximize ESP32 battery life on AA batteries. If we leave that sensor on, it will kill our batteries in days. So I had the AI implement a zero-leakage power management strategy. Our ESP32 Parasitic power circuit design is completely software controlled. The code wakes up, toggles GPIO 10 to physically power the sensor, uses a hardware interrupt to count the pulses for exactly 20 milliseconds, and immediately kills the power. Our sleep current on the probe drops to an absolute 0.0 microamps. But raw frequencies are useless to a human. We need percentages. So I asked the Coder AI to write the math for TLC55 timer frequency to moisture conversion. The AI generated a brilliant implementation using constrained linear interpolation for Arduino sensor calibration. It maps our dry baseline to 0%, our wet baseline to 100%, and forces bounds, checking so our app never reads 105% moisture. Now for the hardest part of IoT design. How do you give a new Wi-Fi password to a completely headless device buried in the mud? You implement a headless Wi-Fi setup for ESP32 IoT devices using a double-tap power cycle. I had the AI write an ESP32 double power cycle detection code leveraging non-volatile storage. When the device boots, it increments a boot count in the flash memory and waits 3 seconds. If you pull the batteries twice rapidly, it sees a boot count of 2, realizes you did it intentionally, and launches the ESP32 Wi-Fi Manager captive portal logic. Now, you just connect to the sensor with your phone, enter your router password to save Wi-Fi credentials to the ESP32 flash memory, or even perform an ESP32 OTA firmware update via Wi-Fi Manager. And if you want to build this exact portal yourself, check out my Ultimate Wi-Fi Manager video linked below. Finally, we need the application facade. The core philosophy of professional firmware is assuming the physical world will fail. What happens if your router unplugs while the sensor is awake? In a standard Arduino sketch, the while loop runs forever, killing your battery. Not here. I instructed the AI to write strict handling for ESP32 Wi-Fi timeouts in deep sleep. We enforce a hard 10-second Wi-Fi timeout and a 2-second sensor timeout. If the Wi-Fi drops or the sensor trace gets severed, the application catches the error, aborts the ThingSpeak transmission, and instantly forces the device back to deep sleep. The ESP32 is basically invincible. With all our native unit tests passing, it was time to flash the final binary to the physical ESP32 C3 hardware. The results were absolutely phenomenal. The double tap triggered the captive portal flawlessly. The over-the-air upload worked perfectly. Manipulating the sensor blade in dry air read exactly 0%, and submerging it in water hit 100% saturation. And the ESP32 ThingSpeak data logging with deep sleep pushed the payload, securely shut down the parasitic power, and went to sleep, drawing practically zero power. By utilizing a highly controlled driver and navigator AI workflow, enforcing test-driven development, and implementing defensive power management, we have successfully built an enterprise-grade C++ firmware package. But our journey isn't over. Now that our electronics and software are bulletproof, we have to protect them from the rain. In Part 3, we're moving away from bulky, ugly junction boxes. We're going to design a sleek, cylindrical, tool-free 3D printed PETG enclosure using a custom hollow rail alignment system. Until then, you can download the entire complete source code the KiCad files, and the BOM from the GitHub repository link below. Subscribe to the channel so you don't miss part 3, and let me know in the comments below. What do you plan to monitor with your new low-power Soil Scout? I'll see you in the next one.